Hi guys, welcome to tutorial 3, Mole Concept and Stoichiometry. Alright, so let's look at question number 1. Constant exposure to mercury is known to produce long-term neurologic effects, especially in children. In Australia, the recommended safe level of mercury in drinking water has been set at 0.001 milligram per liter. Okay, calculate the number of atoms of mercury in 1 liter of water with this concentration of mercury. Now, when they mention about the number of atoms, which means it is about the Avogadro constant. So how to calculate number of particles? Avogadro constants multiplied with the mole. So first we need to find out the mole of mercury in that concentration given, and then we can get the number of atoms. So first of all, we have 0.001 milligram per liter. So this one can be written as 0.001 milligrams in 1 liter. All right. So 0.001 milligrams, you convert it into grams, which is equivalent to 1 times 10 to the power of negative 6 grams in 1 liter. Okay. So this is the mass of mercury in 1 liter. So that is the concentrations allowed. So what you're going to do next is you're going to use the mass in 1 liter divided by the molar mass of mercury. Okay, so when you divide by the molar mass of mercury, you will get the mole. So the answer should be 4.98 times 10 to the power of negative 9. This is the moles of mercury. Okay, so these are the moles of mercury in 1 liter. So the concentration given. All right, so next what to do? Once you've got the mole, I'm going to use 4.98 times 10 to the power negative 9 multiplied with the Avogadro constant. 6.022 times 10 to the power negative 10 to the power of 23. Sorry, no negative. 10 to the power of 23, you will get your answer as 3 times 10 to the power of 15 atoms of mercury. Okay, so the answer for question 1 is 3 times 10 to the power of 15 atoms. Now remember this is all this calculation, it depends on how many decimal places that you use during your calculations. Usually at the end of your calculations, then we will round it up to 3 to 4 significant figures. So it depends on how many significant figures they use, how many decimal places they use. Then at the end, the final answer will have slight difference from the given answer. Okay, so it's about the range, all right, as long as it's not too far from this. This is 3 times 10 to the power 15. If you get an answer of 3 times 10 to the power 14, of course, this is too far. If you get 3.1 times 10 to the power of 15, it's still acceptable, even though it's a big numbers, in fact. All right, so yeah, that's the answer. Okay, if you got different answer, just bring it up. We will discuss it during our sessions. All right, let's look at question 2. Now, under typical summer conditions, a 1 meter cubic volume of dry air has a mass of 1.17 kg. So a dry air has this mass, all right? Assuming that air composed of this percentage of nitrogen, oxygen, and argon. What volume of air will contain 6.022 times 10 to the power of 23? Sorry, guys, this is, I convert to PDF, so this is actually a superscript, which is power 23, which is the Avogadro constant. So what volume of air will contain this amount of atoms in total? Okay, so now here it says that I have 1 meter cubic of air giving you a mass of 1.17 kg, which is equivalent to 1170 grams. Now it's good that to change to gram because at the end of the day, we are converting it into mole. All right, so the molar mass given or the relative atomic mass given in a periodic table are all in the unit of mass, which is gram. All right, so it's good to convert it. So the total mass is 1170. So in 1 meter cubic, you have this total mass of gases, and the percentage of gases are given here. So how do we know the volume of air that contain 6.022 times 10 to the power of 33 atoms? First, we need to find out in 1 meter cubic of air, all right, how many atoms there? How many atoms of gases? Now, different gases is fine as long as we are looking at atoms. So what to do is very simple for nitrogen. Okay, so we're going to use 75.5% multiplied with 1170 gram because this is the total mass of gas in 1 meter cubic. All right, you multiply the mass, you will get the mass of nitrogen itself, and then divided it by 28, which is the molar mass of nitrogen, you will get the mole. Okay, that's the mole of nitrogen molecule. And because they're looking for atoms, so you need to times 2 because one molecule of nitrogen, you have 2 atoms. So the mole times 2, you get a total mole of atoms. All right, and then times with Avogadro constant, you will get the total number of atoms for nitrogen in 1 meter cubic, which is 3.79 times 10 to the power of 25. Okay, now same goes to oxygen. We do the same calculation, just that according to the percentage. 23.1% multiplied with 1170 grams divided by the molar mass of oxygen molecule, which is 32, and then you times with 2 because you have 2 atoms in it, and then do the same thing times with Avogadro constant, you will get the total number of oxygen atoms, which is 1.016 times 10 to the power of 35. Now it depends because, like I said, the decimals they use or the significant figures they use during your calculations, and it will lead you to a slightly different answer. All right, this is just a calculation. So refer to the method, not the final answer sometimes. All right, so argon is just a monoatomic gas. All right, just one atom. So I'm using 1.28% multiplied with 1170. I got the math. Divided by 39.9, which is the molar mass, times 1 because monoatomic, and then times with 6.022 times 10 to the power 33 equals to 2.26 times 10 to the power of 23. Okay, so this will be the total number of nitrogen, oxygen, and argon atoms. So you add them up, you get a total number of atoms in 1 meter cubic. All right, so in 1 meter cubic, total number of atoms is equivalent to 3.82 times 10 to the power of 25. Okay, and then what will be the volume when it is given as 6.022 times 10 to the power of 33? Then you will get your answer here. Now my answer here is around 0.0154 meter cubic. Now, of course, like I said, different decimal, different significant figures will lead you to a slightly different answer. And please clarify with me if your answer is different from mine. And of course, if it is not too far and if you check the methods are all right, then it should be fine. Okay, so this will be answer for number 2. Let's move on to number 3. Okay, around 5000 BC, okay, blah, blah, blah. All right, so the minerals of Malachite is given, a green copper containing mineral. The copper produced was used to make items such as vessel, utensil, religious objects, spearhead, and battle shields. So what mass of malachite will be required to make a battle shield that had a mass of 3.2 kg? First of all, for A, we're trying to convert whatever thing's given into mole. So we're going to use 3.2 kg, which is equivalent to 3,200 grams, divided by the molar mass of copper. All right, so what is the number of mole here? So it should be molar mass 63.5 equals to 50.4 moles of copper needed. So to make a shield of 3.2 kg, 50.4 moles of copper. So this is the amount of copper needed for the shield. All right, so we need to extract the copper from the malachite. So what is the mass of the minerals needed in order to give 50.4 moles of copper? Okay, let's look at this. Now, 1 mole of the mineral, which is Cu2CO3OH2. All right, 1 mole of this will give you 2 moles of copper. Makes sense because you have a 2 here. All right, 1 molecule of this giving you 2 moles of copper. So how many moles of this giving you 50.4 moles of copper, because this is what we want, right? So how many moles of the minerals needed to give that? The answer should be 25.2 moles. All right, so 25.2 moles of the minerals needed to give 50.4 moles of copper. All right, now from this mole of minerals, 25.2 moles, you multiply with the molar mass of the minerals, this formula, just add them up, and then the final molar mass is 221. And then you will get your mass of the minerals needed, which is 5569.2 grams of the minerals, which is equivalent to 5.56 kg of the minerals in order to produce this amount of copper to form 3.2 kgs of the battle shield. Okay, so that is for A. So the 5.56 or 5.6 kg is the mass of the mineral needed in order to produce a 3.2 kgs of pure copper shield. All right, so that's for A, and let's move on to part B. All right, so part B. Explain the advantage of using copper to make items such as those listed rather than using materials like stone and wood. So what are the things that is easier? The advantage of using copper, because it's a metal, so it's malleable. Okay, it's malleable, it is strong, and it's shiny surface. All right, so it looks nice. Yeah, so that this will be the answer for part B. I'm not gonna write it out. So yep. All right, let's move on to question 4. Now calculate the concentration in mole per liter of chloride ions if this mass of aluminum chloride is dissolved in sufficient water to make 250 ml. Now, first of all, we have the mass. Again, we convert that into mole. So first we have 0.581 grams of aluminum chloride, AlCl3. And what will happen is I'm going to use this mass of aluminum chloride divided by the molar mass of AlCl3, which is 133.5. You will get the mole of aluminum chloride, which is 4.35 times 10 to the power of -3. So this is the moles of AlCl3. So in other words, what is the number of mole of chloride ions then? So 1 AlCl3, okay, giving you 3 Cl minus. See that? 3. So which means 4.35 moles of aluminum chloride giving you times 3. You will get the total mole of chloride, which is 0.013 moles Cl minus. So this is the mole of chloride from this mole of aluminum chloride. Okay, so we get a specific mole of chloride. And what next? Because they want concentration in mole per liters. So we're going to use 0.013 equals to MV. V is 250 because this is the volume, over 1000 because volume is in ml, which is cm cubic. You convert it into dm cube or liters. So it's the same. So solve this equation, you will get the concentration of chlorides from this solutions equivalent to 0.052 mole per liter. Okay, so that's the answer for part question 4. Simple, straightforward, all right? Okay, let's move on to number 5. A sample of tap water was found to contain 0.0472 grams of sodium chloride per 250 grams of solutions. So they give you the mass of sodium chloride, they give you the mass of solution. Calculate the concentration in ppm. Now, as we know, what is ppm? ppm is parts per million, which is also known as a milligram per kg of solutions. So in this case, you just need to convert the gram into milligram for the solute, which is sodium chloride, and the mass of solution, you convert it into kg. Then automatically it will be in parts per million. So in this case, what you're going to do is 0.0472, you convert it into milligrams, you're actually getting 47.2 milligrams, okay? Divided by 250 grams of solution means equivalent to 0.25 kg of solutions. Then you will get your answer as 188.8 milligrams per kg. Or you may write your answer as 188.8 ppm. Okay, so it's the same unit here. Straightforward. Number 5, move on. Okay, number 6, the label on the bottle hospital grade disinfectant states that the disinfectant contains 49.9 grams per liter of sodium hypochlorite, NaClO, and 12 grams per liter of sodium hydroxide. Now, I noticed that from some of you in the tutorial question posted in Open Learning, this question was incomplete, the one posted on it. They miss out the compound. It's supposed to have 2 sources of sodium ions in this case. So this is the complete one. So I'm going to show you what are we going to do. Now, I have 49.9 grams per liter of NaClO. All right. And then we have 12 grams per liter of NaOH. And what they want is calculate the concentration in mole per liter of sodium ions. So what they want is just the sodium ions. All right. So they want mole per liter. We need to calculate the mole. All right, so let's start with 49.9 grams in 1 liter of NaClO. So in 1 liter of NaClO, you're expected to have 49.9 grams of NaClO, right? And then we are going to divide by the molar mass, 49.9 grams of NaClO divided by the molar mass of NaClO, 23 plus 35.5 plus 16, all right? And then you get a mole. So the mole is 0.669 moles. 669 moles of what? NaClO, which is equivalent to 0.669 moles of sodium plus. Make sense? Because one molecule of this should have 1 sodium. So if you have 0.669, you should have 0.669 moles of sodium ions. Okay, now same thing goes to 12 grams in 1 liter of NaOH. All right, so 12 grams divided by the molar mass of NaOH, 23 plus 17, and then you will get the mole. The mole from here is 0.3 moles of NaOH. So how many moles of Na in 0.3 moles of NaOH? Same thing, 0.3 moles of Na. Because one molecule of this, you have 1 Na. So same. And then what next? Total up the moles of sodium ions. Okay, insufficient space. I'm going to erase that. You total up the mole, 0.669 plus 0.3. All right, so let's erase that. We have 0.969 moles of sodium ion. That's the total. Okay, then what to do? So all per liters, right? All the while we are doing in the bottles of 49.9 grams per liter, and sodium hydroxide is also per liter. So everything, this one should be in 1 liter. So the concentration of sodium ions, which is 0.969 mole per liter. Okay, so that's the answer. Again, 0.969 is just 3 significant figures. If you get something different, but not far from it, it should be fine. Check the method rather than the final answer sometimes. Okay, as long as it's not far away from it. If it is too far, all right, then might be something wrong, right? Number 7. Okay, let's look at number 7. The concentration of calcium in milk is 0.114%. M/M. What does that mean by M/M? So it means 0.114% by mass of calcium. So in the total mass of the milk, for example, the milk having 100 grams, for example, 0.114 grams is actually from the mass of calcium. Okay, the rest are actually water or other components inside, or other minerals inside, or other vitamins. All right, so in milk, if you have 100 grams of milk, you should have 0.114 of calcium. So that is what it means by mass/mass, percentage by mass. All right, so I have 0.114% by mass of calcium. All right, and then the amount of calcium consumed by a teenager is 1,300 milligrams. So we need 1,300. How many glasses of milk will need to be consumed to achieve this recommended daily amount? So assume that the volume of glass is 250 ml. All right, one glass is 250, and 100 ml of milk has a mass of 103 gram. Okay, that's a good important information. So 100 ml. All right, so 100 ml of milk is having 103 gram. This is the mass of the milk. So from here, we know that 0.114% of this 103 is actually the mass of calcium, which is equivalent to 0.1174 grams in 100 ml of milk. Makes sense? So in 100 ml, I have 103. So out of 103, 0.114%, which is 0.1174 grams, is actually the mass of calcium. Okay, so this is mass of calcium. All right, in 100 ml of milk. So what to do next? One glass is 250. If 100 ml giving you this mass, so 250 ml, what is the mass of calcium? It should be 0.294 grams. Okay, so in 100 ml, you have 0.1174. In 250, you should have 0.294 grams of calcium. For one glass, you have 0.294 grams of calcium. And one day, we actually need 1,300 milligrams. Again, so 1,300 milligram is equivalent to 1.3 grams. This is what we need. Divided by 0.294 grams. This is the mass of calcium in one glass. Then we will know how many glasses. So the answer is 4.4 something. Okay, 4.4, which is approximately 5 glasses. Okay, we can't put 4 because it's slightly more than 4, so we have to put it as 5 glasses. So if you drink 5 glasses of milk, according to the calculations, according to the percentage by mass of calcium, 5 glasses of milk will give us enough calcium per day. All right, so in this case, this is the answer for number 7. Okay, let's look at number 8. 500 ml of distilled water was added to 320 ml of 5.33 mole per liter sodium hydroxide. You are adding water into a solution of sodium hydroxide. What does it mean? When you add water into any solutions, unless you're adding back into water, into any solutions, that's dilution. Okay, so if it is the dilutions, we have to use the formula M1V1 equals to M2V2. So M1 usually the original concentration, which is 5.33. V1 is original volume, which is 320, equals to M2, the final diluted concentration. And the final volume, we should add up 320 plus 500. So you have 820. This is the total final volume. And from here, we get M2 equals to 2.08 mole per liter. See that? The concentration is much lower now because we are adding water. We dilute it. So we got the concentration of the NaOH. Now what they want, the mole of hydroxide ions will be present in 20 ml of these diluted solutions. We have concentration, we have volume, we can calculate the mole. What is the formula? So mole equals to 2.08 mV, which is 20 over 1,000. You will get the mole of NaOH, which is 0.0, mole equals to 0.0416 moles. This is the moles of what? This is the moles of NaOH, which is the same, okay, which is the same, the mole of OH minus. Again, one NaOH giving you one OH, so the mole should be the same in this case. So 0.0416 moles of hydroxide ions. That's the answer. All right, so this is number 8. Let's move on to number 9. Okay, 50 ml of 0.126 mole per liter nitric acid is mixed with 70 ml of 0.429 mole per liter of nitric acid. Now, both are nitric acid. You're going to mix them together. Of course, they both having different concentration and you're adding different volume. So what I'm going to do is, first, we calculate the mole for each nitric acid. Okay, the mole from here, the first nitric acid, and the mole from here, the second nitric acid. We get the separate mole. we add them up using the total volume to calculate the final concentration. So what we're going to do here is I calculate the mole of this, which is 0.126 times 50 over 1000, MV over 1000, guys. So what do you get? I'm getting 6.3 times 10 to the power of -3 moles. This is the first nitric acid, and from here 0.429 times 70 over 1000, and you will get the mole 0.03. So I have 0.03 plus 6.3. Make sense? So total mole, add them up, you will get 0.0363. This is the total moles of nitric acid, HNO3. All right, and then what is the concentration? I have the mole, 0.0363 moles equals to M. What we want, volume supposed to be the addition of both, 50 plus 70, so you get 120 over 1000. You will get your answer M as 0.3 mole per liter. And they want your answer in gram per liter. How to change it into gram per liter? From mole to gram, you just need to multiply with the molar mass. Okay, molar mass of what? Molar mass of nitric acid. Make sense? So you times it with the molar mass of nitric acid, automatically your answer will be in 19.1 gram per liter. You will convert it in from mole per liter to gram per liter. So this is the final answer for number 9. Okay, number 10. Concentrated hydrochloric acid has a density of 1.16 gram per milliliter. Okay, 1.16 gram per ml. All right, and it contains 32% of mass of hydrogen chloride, which means, guys, if I say concentrated hydrochloric acid, okay, which means I have majority of hydrochloric acid, but small percentage of water, then you get a concentrated hydrochloric acid. It's not 100% pure hydrochloric acid. That's why they mention concentrated. If it is pure, means they should mention pure hydrochloric acid. So from here, we know it's a mixture of HCl, majority, with some water, then you get a concentrated hydrochloric acid. And the density is given here. Now, it's split into two parts. First, we have a density of HCl, which is 1.16 gram in 1 ml. Make sense? In 1 ml of concentrated hydrochloric acid, you have 1.16 grams. Okay? In 1 ml of concentrated hydrochloric acid, the mass is 1.16 gram. But is this 1.16 equivalent to all the mass of hydrochloric? No, it's 32%. So from here, we're going to use 32% multiplied with 1.16. You will get the actual mass of HCl in it, which is equivalent to 0.3712 gram of HCl in 1 ml. All right, that's the first part. In 1 ml, this is the mass of HCl. All right, next, what do we need to prepare? We need to prepare this amount of HCl solutions. So from here, we can calculate the mole of HCl needed. What we need to prepare. All right, so it's 2 MV times 500 over 1000. You will get the mole. So it's equivalent to 1 mole. So we need to prepare 1 mole of HCl. 1 mole is equivalent to 36.5 grams of HCl. So we need to prepare 36.5 grams of HCl, and we know that 1 ml consists of 0.3712 grams of HCl. So from here, what is the volume of the acid needed in order to give 36.5? So you're going to use 36.5 is what we want, divided by 0.3712 grams, all right? And then we will get the volume needed, 98.3 ml. Okay, so this is the volume of concentrated HCl to have or to give 36.5 grams of HCl, which is what we want. And if this is the volume of the acid needed and the total volume is 500, so what is the volume of water? Now, this is for HCl. So what is the volume for water? which is 500 minus 98.3. You get the volume of water, which is equivalent to 401.7. Okay, so this is the ml. So the answer is 401.7 ml, 98.3 ml with water and HCl respectively. Okay, so this will be the answer. 11. Okay, now a mixture of 0.129 grams of potassium chloride and 0.452 grams of aluminum chloride is dissolved in water, and more water was added to make up the total volume equals to 500 ml. Okay, so total volume is 500 ml. Calculate the concentration in mole per liter of chloride ions. So they just want chloride ions as usual, guys. 0.129 grams of KCl divided by the molar mass of KCl, you will get the mole. And the mole here equals to 1.73 times 10 to the power of negative 3 moles of KCl. This is the mole of KCl, which is the same for the mole of 1.73 times 10 to the power of negative 3 moles of chloride. So this is the moles of chloride. All right, this is for KCl. And then I have 0.452 grams of aluminium chloride. The formula is important. Divided by the molar mass, you will get the mole. And the mole here is 3.39 times 10 to the power of negative 3 moles of aluminium chloride. And how many moles of chlorides here? You need to times 3. So 3.39 times 3, you will end up getting 0.01 mole of chlorides. All right, so this will be the total moles of chlorides. You add them up, 1.73 times 10 to the power negative 3 plus 0.01. So again, insufficient space, I'm going to erase that. All right, so the total mole of chlorides equivalent to 0.01173. Okay, so this is the total mole of chlorides, and we need to prepare 500. So 0.01173 moles, use the formula, equals to MV. M is unknown, V is N up, you get 500 ml over 1,000. And you will get your final concentration equivalent to 0.0235. Okay, to 0.024 will do mole per liter. Because they want concentrations of chloride ions, and this is the one. Simple, right? Okay, now that's question 11. Let's move on to question 12. Okay, now look at 12a. When aluminum is heated strongly with iodine, the following reactions occur. What mass of iodine will be required to form 128 grams of aluminum iodide? If you look at the equations, whenever they give you equations or more than one compound involved, it's good that you write out the equations so that you know you need the balance equation. Otherwise, the mole ratio would lead you to the wrong answer. All right. So now, aluminum iodide, you need to prepare 128 grams of aluminum iodide. This one need to be 128 grams. I need to prepare this. Okay. So what is the mass of iodine needed? Okay, let's solve part A. So first, we need to calculate the mole of aluminum iodide. I given with 128 grams over the molar mass, which is 407.7 AlI3. You will get the mole of 0.314 moles of aluminum iodide. All right, that's the mole. And what is the mole ratio of AlI3 to I? To iodine. From the equation is 2 to 3, right? So 2 AlI3 forming 3 iodine is what I want. So the ratio is 2 to 3, which means I'm going to use 0.31, sorry. .314 of aluminum iodide multiplied with 3 over 2. Okay, times 3 divided by 2. You will get the mole of iodine, and the mole of iodine here is supposed to be 0.471 moles of iodine. So this is the mole of iodine needed. Okay, but they want mass. So I'm going to multiply it with the molar mass, okay, which is equivalent to 126.9 times 2 because I2. All right, and the final mass of iodine is 119.5 or 120 if you want it. So this is the final answer for A. Okay, the mass of iodine needed to produce 128 grams of aluminum iodide. We're going backward on that. All right, so next we're going to erase that, and we're looking at part B then. So B, acid react with marble chips according to the equations given. Okay, again, check the mole ratio, and then what volume of 2.17 mole per liter of hydrochloric acid will be required to react with 10.5 grams of marble chips. So what is the volume of hydrochloric acid needed? First, I'm given with 10.5 grams. So 10.5 grams of marble chips, which is calcium carbonate, divided by the molar mass of calcium carbonate, which is 100.1. You will get the mole of calcium carbonate, which is 0.105 moles of calcium carbonate. And what is the ratio of calcium carbonate to acid? HCl means this lah. So it's 1 to 2. So this is the mole of calcium carbonate. What is the mole of acid? 0.105 times 2. I get the mole of acid, which is 0.209 moles of acid, which is HCl in this case because they just take out the Cl minus. Okay, so I have I need 0.209 moles of H, which is the acid needed, and I'm given with the concentration. They are looking for volume, so very easy. 0.209 moles equals to mV over 1000, and m is 2.17. Volume is what we want, over 1000, 0.209. And from here, you will get a volume equivalent to 96.3 ml. Okay, solve the equations, you will get 96.3 ml. So this is the volume of acid needed from the mole. Okay, always check the mole ratio when you're comparing two or more compounds. All right, this is question 12. Okay, sulfuric acid for question 13. Calculate the mass of sulfuric acid that can be produced. They want to know this, the mass. All right, from where? From 3.7 tons of iron pyrites, FeS2, sorry. So from here. So how many tons we have? 3.7 tons. All right, so what to do next? I have 3.7 tons divided by the molar mass of FeS2, all right? Molar mass of FeS2. Don't times 4 for the molar mass, guys. No, don't times 4 for the molar mass because molar mass means for one molecule per mole, all right? So what is the molar mass here? Should be 119.8. Okay, if you calculate that, so I just put it in for your reference. 119.8, this is the molar mass of FeS2, all right, iron pyrites. And then you will get the mole. The mole is 0.031 moles of iron pyrites, FeS2. Now from the equations here, now we have to look at the ratio because this is a continuous reactions, step 1, 2, 3. So we're going to do 4 mole of FeS2 produce 8 moles of SO2 because SO2 is going to be start here. So from here to here, you just need to times 2. Therefore, from here I times 2, I get 0.062 moles of SO2. All right, and from 8 to 2, don't ever compare between the 8 here and the 2 here because these are two separate equations. The mole ratio only compared within a single equation. So from 8 to 2, we don't care. So we have 0.062 moles of SO2, which is starting from here, 0.062. All right, so 0.062 convert to SO3, 2 to 2 means 1 to 1. So at the same time, I'm getting 0.062 moles of SO3 because it's 1 to 1. And what happened? I have 0.062 of SO3. How many more of sulfuric acid? 1 to 1, which means I have 0.062 moles of H2SO4. All right, and once I got a mole, it's very simple. It's just 0.062 multiplied with the molar mass of sulfuric acid, which is 98. That's the molar mass, all right, of H2SO4, and then equivalent to 6.08 tons. Now, you may be asking now, why am I getting tons straight away? Now, see, from here, 119.8 is actually the molar mass in grams, right? Gram per mole. And this is in tons. We're supposed to change it into mass, right? Now, see, if I chose not to change this ton into gram, when I still divide it, I will still get the mole. So at the end, when I multiply it with the molar mass of a compound again, the final unit that we got should be in ton as well. Which means, in other words, if I convert the tons here initially into gram, at the end, we will get the answer in gram. If you don't convert it, then at the end, we get back the same thing, which is ton. Because when you divide a molar mass and you times a molar mass again, although it's different compound, you will get back the same unit. You get it? So if you choose to be in tons, then no points converting it, because at the end of the day, you still have to convert it back into tons. So might as well just do it in tons to get the mole, and from the mole, it's just a ratio, and then you will get the tons at the end for your answer. Okay, hope you can get that. If you're confused, let me know during the sessions. So this is for question 13, 6.08 tons or 6.1 tons. If you round it up, it's fine. Okay, let's move on to 14. Okay, 0.782 grams of pure magnesium was added to 50 ml of the 1.54 mole per liter of HCl solutions. Now, they give you the mass of magnesium as well as the concentration and the volume of HCl, two compounds reacting here. What volume of NaOH solution will be required to neutralize the hydrochloric acid left over from the reaction? What does that mean by leftover? Which means from the first equations here, the acid is actually in excess. Makes sense? Because if you react with the stripe of magnesium and you still have some leftover, which means your magnesium is the limiting reagents and your acid is in excess. And they want to know how much of NaOH needed to neutralize the remaining HCl. So how to know that? First, we need to calculate the remaining HCl in terms of mole. All right, so let's do that. First, we calculate the mole of magnesium, which is this. So 0.782 grams of magnesium divided by 24.3, the relative atomic mass, you get the mole 0.032 moles of magnesium. Okay, I have the mole of magnesium. Next, I'm going to calculate the mole of the acid in the solutions, which is in excess here. What are you going to do? 1.54 mV over 1000. I get the mole of HCl, which is the acid. I got 0.077 moles of HCl, or the H acid here. Okay. Now come back to the equations here. I don't want to confuse. So look at that. Once we got the 2 moles here, all right. So we need to know, although we know that this is stuff definitely in excess, so we need to check the ratio. All right. So what we're going to do now? We need to know how many mole of acid will react with the mole of magnesium here, which is the limiting reagent. So in other words, 0.032 moles of magnesium required how many mole of HCl to react with it? Very simple. So what is the mole ratio here? 1 to 2. So if I have 0.032 moles of magnesium, how many mole of acid needed? 0.032 times, right? You get 0.064 moles of HCl needed. Okay, you need 0.064. And how many moles of HCl in the solution? We have 0.077. We have this, and we need only 0.064. Make sense? So I'm going to use 0.077 minus what we need to react. You will get the remaining of HCl, which is 0.013 moles of HCl remaining. Make sense? So this is the amount of moles of HCl remaining. All right. So let's continue. Insufficient space again. I'm going to erase all. So we have 0.013 moles of HCl. Okay. Let's look at this equation. If I have 0.013 moles of H plus, which is the acid remaining, how many mole of OH needed? 1 to 1 ratio. So which means I need 0.013 as well. Make sense? So if I need 0.013 mole of OH minus equals to MV over 1000, M is 0.285. This is what they give. And we are looking for the volume of NaOH needed to neutralize it. So what is the volume here? The volume here, you solve it, you will get the volume of NaOH needed to be 45.6 ml. Okay, or you can put it as 0.045 liters. Now it's up to you whether you leave it as liters or ml, unless they're specifying in the questions. All right, so this is the final answer for question 14. All right, 15. If 4.63 grams of methane, CH4, is introduced into an evacuated 2-liter container at a temperature of 35 degrees C, what is the pressure of the container? Now I have the mass, I have the volume, I have the temperature. So what we're going to do is just put into PV and RT, ideal gas equations. Now, before I do any calculations, make sure you know this. Pressure can be in Pascal or kilopascal. Volume, you need to follow. If it is in Pascal, the volume needs to be in meter cubic. Meter cube. If it is in kilopascal, then the volume will be automatically in dm cubic, which is equivalent to liter. All right, so either meter cube or dm cube or liter. Make sense? Okay, done with this. We're going to put in the informations, the value, so we can calculate, get the answer. All right, so then what is the pressure needed? So P is unknown. What is the volume given? 2 liter. Now still remember, 2 liter means 2 dm cube. The pressure obtained will be in kilopascal then. All right, equals to N. N is the number of mole. How to get 4.63 grams over the molar mass of CH4, which is 12 plus 4, 16. Okay, this is the mole. And then R is 8.315, gas constant. And then temperature is 35 plus 273. They need to be in Kelvin. All right, so from here, solve the equations. You will get your pressure as 370 kilopascal. Why is it kilopascal? Because volume is in liter. All right, so that's for 15. Moving on, 16. All right, in the lab, 56.4 ml of dry sulfur dioxide gas at a temperature of T and 98 kilopascal pressure was dissolved in hydrogen peroxide solution, convert all the sulfur dioxide into sulfate ions. Now, sometimes it may be confusing when you look at the questions, especially those long questions, because too many compounds involved. And sometimes they use some terms that is confusing as well, or it's some things that you never heard before. Okay, it doesn't matter. So the most important is, like in this case, they can be complicated, but they give you the equations, right? So the ratio is important, the mole ratio. the balance equations, and then you can get whatever you want at the end. Addition informations, additions of excess barium chloride solutions to resulting solutions. Now, if you add barium chloride into the resulting solutions, into these solutions, which one will react with the barium? See here, they said barium sulfate precipitate. See that? When I add this in, the barium will react with the sulfate to give you a white precipitate. All right, so in that case, I have 0.521 grams of barium sulfate divided by the molar mass of barium sulfate, okay, which is 233.3. All right, this is the molar mass, and you will get the mole of barium sulfate, which is 2.33 times 10 to the power of negative 3 barium sulfate. Moles, huh? All right. So if you have 2.33 times 10 to the power negative 3 moles of barium sulfate, how many moles of sulfate is that? Because you're producing sulfate here in the solutions. One barium sulfate produces one sulfate. So same thing, I should have 2.33 times 10 to the power negative 3 moles of sulfate ions. All right, 1 to 1. So now we got the mole of sulfate. Okay, so if we get the mole of sulfate from the equation 2.33 times 10 to the power of negative 3. So this is the mole of sulfate. So how many mole of sulfur dioxide is expected? What is the ratio here? 1 to 1, right? So this one is expected to have 2.33 times 10 to the power of negative 3 moles as well. Now we got the mole of sulfur dioxide. Okay, and with all other informations, we're going to sub into the PV and RT equations, which is what I'm going to do now. PV equals to nRT. All right, and what is the pressure here? 98 kilopascal. Volume, when they give kilopascal, your volumes will be in dm cube or liter. So 56.4 ml equivalent to 0.0564 liter. All right, equals to N, which is the number of mole of sulfur dioxide, 2.33 times 10 to the power negative 3. This is what we got just now. And R is constant, 8.315. Temperature is what we want. All right. And then from here, you solve the equations. You will get your temperature as 298.1 Kelvin. Okay. And what they want here is in degree C. See that? So what is the temperature of T in degree C? You just minus 273. You will get 25.1 degrees C. So this is your T then. Okay, from the mass of the solid, calculate backwards to get the sulfate. From the sulfate, you get the mole of sulfur dioxide, and then you sub into the PV and RT, you will get the temperature in the reaction or during the reactions. All right, that's 16. Let's look at 17. When 3.4 liters of propane burns in excess of air, what volume of carbon dioxide will be formed, assuming the volumes are measured? Now, this is important. They're measured at same temperature and pressure. What does that mean by same temperature and pressure? Which means it can be STP, it can be RTP. It doesn't matter. Which means before the reaction, let's say, for example, you measure that under STP. Okay, before the reaction, which is the propane. At the end of the day, at the end of the reactions, you got the carbon dioxide gas and you also measure it under STP. What does that mean is the molar volume will be the same. If you're using STP, then it will be 22.4. Same for both. If you're using RTP, then it will be 24 dm cube. So it's the same here. All right. So what I'm going to do here is propane is C3H8. Okay. You add oxygen, you get carbon dioxide and water. This is combustion equations. And then automatically you balance it. You will get 3 carbon dioxide, 4 water, and up you get 5 oxygens. All right. So if I'm burning 3.4 liters of propane in excess of air, so this one is in excess. This is LR. If this is LR, means the 3.4 liter will be fully burned and convert into carbon dioxide against water. Make sense? So they want a volume of carbon dioxide. Now, how to know the mole here? The mole ratio is C3H8 to carbon dioxide gas is 1 to 3. See that? 3 here, 1 here, of course. All right. So the ratio is 1 to 3. So usually I will do that. If it is STP, I'm going to use 3.4 liter over 22.4 liter dmq, right? You get the mole. And from the mole, you times 3. Okay, you will get the mole of carbon dioxide. From the mole of carbon dioxide, all right, and you times it with 22.4, you will get the volume again. See that? I divide by 22.4 here, I multiply with 22.4 here. So end up, the whole process is just 3.4 liter times 3. So the final answer, the liters here is 10.2 liters. You make sense? Divide by 22.4, you get a mole, mole times 3. End up, I still have to multiply with 22.4 again. So divide and multiply, cancel out the 22.4. Straight away, you use 3.4 liters times the mole ratio of 3, you get 10.2 liters. That's the straightforward answer. All right, so 18. Okay, look at 18. 0.12 grams of aluminium is added to 6.38 ml of 2. Sorry guys, this is a bit weird. Should be -1. So this is concentration. Okay, 2.03 mole per liter. And this is the volume, obviously. The mass of aluminium. All right, aluminium and acid. And the evolved gas, referring to hydrogen, is collected at this temperature, and this is power 5, guys. 10 to the power 5, sorry, Pascal. So what volume of hydrogen will be produced? They give you the mass and also the concentration for both. We need to identify the limiting reagents. All right, we need to identify the limiting reagents before we know the amount of hydrogen gas produced. So one by one. For aluminium, 0.12 grams divided by 27, the molar mass of aluminium, and you will get 4.44 times 10 to the power of -3 moles. Okay, and for acid, 2.03 MV/1000, 6.38 over 1000, you will get the mole of acid. So the mole of acid is 0.0129 moles. Okay, now how do you know which one is excess, which one is limiting? The ratio is 2 to 6, so we have to do this. I'll always do that if you follow. I'll take the smaller one. Between these two values, which one is the smaller one? This one. I'll take this. Okay, you ask yourself, 4.44 times 10 to the power of -3 moles of aluminium required how many mole of acid? 2 to 3 means the ratio is multiplied by 3. Sorry, let's come back again. Let me pause. Okay, let's continue here. Now, yeah, if I have 4.44 times 10 to the power -3 moles of aluminium, how many mole of acid, which is the H plus required? Ratio is 2 to 6 means times 3, right? So I need 4.44 times 10 to the power -3 times 3. You will get the mole of acid required. So what is the mole of acid required? You times 3, you will get 0.0133 moles of acid, H plus required. Okay, so this is the mole of acid required. But how many moles of acid we have in the solution? 0.0129. And what we need is 0.0133. What does that mean? I have less than what we need, right? I have less than what we need. So which means your acid is the limiting reagent. Agree? So if you have less than what we need, which is 0.0133, then your acid is the limiting reagent. So whatever product produced is based on the limiting reagent. All right, so I have 0.0129 moles of acid. This is the limiting reagent. It's all based on that. Let's erase the rest. Okay, now this is the LR, limiting reagent, which is 0.0129 moles. This is what we have. Of course, we need 0.0133, but we don't have that much. We only have 129, so all based on this. And if that's the case, how many mole of hydrogen produced here? The ratio is 6 to 3, which means divided by 2, right? So this value divided by 2, you will get the mole of hydrogen produced. So 0.0129 divided by 2, you get 6.45 times 10 to the power of negative 3 moles H2 produced. So this is the mole of hydrogen gas produced based on ATL. Okay, then we're going to sub into the PV and RT. So PV equals to nRT. P is 1 times 10 to the power negative 1 times 10 to the power of 2. I change it into kilopascal. And the volume will be in dm cube at the end. Okay, so the mole is 6.45 times 10 to the power negative 3, 8.315 times temperature, 24 plus 273. Don't forget to add 273 because it's in Kelvin. And the volume needed at the end should be in liters, so 0.159 or 0.16 liter. So this is the volume of gas produced. Okay, please check again the method of comparing to get the limiting reagent. That's very important. Let's move on. 19. All right, question 19a then. The mass of precipitate form. Let's check that. Unfortunately, equation is not given in this question. We have to come up with our own equations. So is a reaction, precipitation reactions between copper chloride with sodium phosphate. All right, and then what do you get? You just exchange the positive and negative ions. Just exchange the ions, you will get the product. So in this case, you should have copper phosphate. Okay, copper is 2 plus, phosphate is 3 minus. That's why you get 3 and 2 here. And then the remaining will be sodium and chlorine. So it's sodium chloride. All right, next thing, balance equations. All right, so you will need, see, I have 3 here, the complex one. Please solve the complex one. I have 3 here, which means I will definitely need 3 copper chloride in order to give us 3 copper. Okay, and I have 3 sodium here. So I have 6 chlorine, which means I have 6 here. And then you will get 2 times 3, you get 6 sodium. Yeah, right? So this is the balance equation, 3, 2, 1, 6. Next, calculate the mole for each and identify the limiting reagent. So one by one. So what is the mole of copper chloride here? Based on the information given, this is the one. MV or 1000, 0.175 multiplied with 23.9 over 1000. You will get the answer as 4.18 times 10 to the power negative 3 moles. Okay, and what is the mole of sodium phosphate? This is the information. 42.6 times 0.251 MV or 1000. Oh, sorry, just 1000, guys. And then you will get the mole here, 0.0107. Okay, and once we got the mole for both sides, next, we're going to take the smaller one, which is this. Right? So if I have 4.18, it's up to you guys. You want to take a bigger one, that's up to you. But my way, I will take the smaller one. So I have 4.18 times 10 to the power negative 3 moles of copper chloride. So how many more of sodium phosphate required to react with copper chloride? How many more of this required to react with this amount of copper chloride? So the ratio is 3 to 2. All right, the ratio is 3 to 2. So what we're going to do is I'm going to use 4.18 times 10 to the power negative 3. All right, 3 to 2 ratio. So I divide by 3 times 2. You will get the mole of sodium phosphate required, which is 2.78 times 10 to the power of negative 3 moles required. Okay, so I require this mole of sodium phosphate. All right, and then we check how many mole of sodium phosphate we have in the solutions. 0.0107, and I need only 2.78, which means sodium phosphate in excess. All right, and therefore copper chloride is the limiting reagent. Is that clear? So this is copper chloride limiting reagent, and the mole here is 4.18. All right, so let's continue. I have 4.18 here. I have 0.0107 moles of sodium phosphate. Let's continue to check the mass of precipitate form. So what is the mass of precipitate form? Which one is precipitate? Obviously, sodium chloride is soluble. So this will be the precipitate. Okay, so if I have 4.18 times 10 to the power negative 3 moles of limiting reagent, the ratio is 3 to 1. So I need to divide by 3. Okay, so when I divide by 3, this one divided by 3, divide by 3, you will get the mole of copper phosphate, which is 1.39 times 10 to the power negative 3 moles. Once you got this, what to do? You multiply it with the molar mass of copper phosphate is 380.5, and then you will get a mass of copper phosphate, which is 0.528 grams. So this is the answer for part A. Okay, and part B. This is a bit tricky here. Let's continue with part B. Let's erase everything. I'll rewrite the equations because we will need that. Copper chloride plus with sodium phosphate forming copper phosphate, which is a precipitate here, a solid, and then we have NaCl, right? 6, 2, and then 3, all right? So balance equation done. We look at B now. And what is the mole? Of course, we need to write out the mole just now. This is the mole 4.18 times 10 to the power negative 3. What is the mole for sodium phosphate? In excess, 0.0107. Okay, it might be not clear here. I think the most important is write it clearer, so otherwise you will confuse. 0.0107. All right, now that's the mole from the respective compound, and we know that this is it in excess. All right. Okay, now next, what is the mole of sodium phosphate required? Just now we calculate from here. This mole I divide by 3 times 2. I will get 2.78 times 10 to the power negative 3. This is the mole of sodium phosphate required. Okay, this is required, and this is what we have. We need all this information because the question asks, calculate the concentration of each of the ions remaining in the solution after the reactions. Now, what does that mean by ions remaining in the solutions? Ion remaining means we are not looking at the precipitate. So the precipitate, whatever ions that already formed the precipitate, which is this one, is not being counted, no. So copper is from limiting reagent. So all the copper converted into solid. So there's no more copper ions in a solution. Ignore copper ions. Okay. And another thing from the solid is the phosphate, PO4. Do we have extra phosphate? Where does the phosphate comes from? The phosphate comes from sodium phosphate, and which is in excess. So what will be the remaining phosphate here? What will be the remaining phosphate here? So the mole of remaining PO4, 3 minus, the phosphate ion will be 0.0107. This is what we have, minus what we required. You will get the mole of phosphate to be 7.92 times 10 to the power of negative 3. That's the mole of phosphates remain? Okay, we have the mole of phosphate remains. That's 1. Okay, what else? What are the ions present in the solution? Phosphate, we have this remain, and we have NaCl. See that? We have NaCl. Where does the NaCl comes from? Na is from here, Cl is from here. One by one. What is the mole of Cl minus? From here, right? All the Cl here converted into a soluble NaCl. So what is the number of mole of Cl here? 4.18 times 10 to the power negative 3. Because of 2 here, we need to times 2. So 4.18 times 10 to the power negative 3. This is the mole of copper chloride. Because I have 2 chloride in it, so I times 2. I get the total mole of chlorides in the solution, which is 8.36 times 10 to the power negative 3. This is the moles of chlorides. Okay, I got the mole of chlorides here. Done. What about the mole of sodium? The same thing, guys. The mole of sodium is from here, okay, and it's already in excess. So this is required. All right, this is what we have. But the sodium did not convert into a solid. See that? Sodium from here, they convert into NaCl, which is also soluble. So we take the total sodium ion, which is 0.0. 107. Okay, so this is the total sodium ions that we use, which are not converted into that. So we're going to times how many? 1, you have 3, so 0.017 times 3. Okay, so 0.0107 times 3, you will get, because this is the total ions we have, 0.0107 times 3, you will get the mole of sodium ions. All right, let me calculate. You will have 0.0321 moles of what? Sodium plus. See that? Yeah. So you have all these moles. Now, what they want is concentrations. So you have to convert them into concentration. So how to convert them into concentrations? Very simple. I'm just showing you one of it. Okay, let's say 0.0321, right? I have to erase that because, I just erase all. Remember the moles here, all right? 0.0321 moles of sodium. 0.0321 moles of sodium. This is the sodium ions in the solutions, right? What is the total volume of solutions after you have added both together? 23.9 plus 42.6. Okay, so what is the total volume? 66.5 ml. All right, so I have molar volume, 0.0321 equals to mv 66.5 over 1,000. So your m is equivalent to the concentration of sodium. So this is how you calculate to get the concentration of sodium, and do the same thing. The volume will be the same for all. So take the mole from each ion just now, sodium, phosphate, and chlorides. Phosphates are like strong, chlorides. Take the mole for each, do the same thing here, MbO 1000, you will get the concentration for each ions. Okay, so this until this stage, I believe you can calculate yourself. For the next thing, I think the video is a bit too long. Let's continue. Question 20. 0.7 grams of potassium hydroxide was dissolved in 50 ml of 0.8 mole per liter. Again, guys, my apologies, it's -1 per liter of sulfuric acid. Calculate the concentration of sulfuric acid in the mixture after the reactions. When they say calculate the concentration of sulfuric acid, which means they give a hint here. The hint is the sulfuric acid is in excess, because after the reactions, you still have some remaining of sulfuric acid. Make sense? So let's check it out. what is the concentration of remaining sulfuric acid. So first, write out the balance equation, KOH plus H2SO4. Okay, KOH plus H2SO4. You will get the equations, H2SO4. You get K2SO4 plus H2O. So it's a neutralization reactions, guys. It's neutralization reactions. Balance equations. I need 2 KOH. I'll form 2 water. Okay, balance. Next, we're going to calculate the mole for each compound, the reactants. 0.7 grams over the molar mass, 56.1. You will get 0.0125 moles. Okay, for sulfuric acid, 0.8 multiplied with 50 over 1000, you will have 0.04 moles. Again, I'm taking the smaller one, which is this, to compare and check how much of sulfuric acid needed here. How many moles of sulfuric acid needed? If I have 0.0125 moles of KOH, how many more sulfuric acid needed? You just use this mole and the ratio is 2 to 1. So divide by 2. 0.0125 divided by 2, you get 6.25 times 10 to the power of -3. This is the moles of H2SO4 required to react. This is the amount that we need. And this is the amount that we have. Obviously, is in excess. So proven that sulfuric acid is in excess. But the question is, how many more of sulfuric acid remain at the end of the reactions? Just use 0.04, what we have, minus 6.25 times 10 to the power of -3. You get the remaining mole of sulfuric acid, which is 0.0338 moles. This is the moles of acid remaining. Okay, and what next? 0.0338 equals to mv. What is the volume here? 0.7 grams is a solid. Volume is still maintained as 50. So still 50 here over 1000. All right, and then from here you get your m. This is your answer, which is 0.676 moles per liter. So the concentration of sulfuric acid remaining at the end after the reaction is 0.676. All right, so that's 20. Let's look at 21. An excess quantity of zinc metal is placed in the solutions containing 125 ml of concentrated nitric acid. Assuming all nitric acid reacted with the zinc, determine the mass of zinc that reacted. Okay, let's write out the equations for the whole thing. Zinc is in excess plus HNO3. All right, you will get zinc nitrate plus hydrogen gas. Okay, 2 nitric acid. So this is the balance equations. And what are we going to do? Excess of zinc, we can ignore that. So we calculate the limiting reagent, which is nitric acid. So 6 MV/1000, 6 is the concentration. 125 over 1000, you get the mole, which is 0.75 moles. So they said all nitric acid reacted. What is the mass of zinc that reacted with it? If I have 0.7 moles of nitric acid, how many more of zinc needed to react with it? It's already in excess, so we calculate the amount needed. So ratio is 2 to 1. All right, so divide by 2. So 0.75 divided by 2, you get 0.375 moles after divided by 2. So this is the mole of zinc needed, and you multiply with the molar mass of zinc, which is 65.4. You will get the mass, which is 24.5 grams of zinc needed. So this is the answer for A. Mass of zinc reacted, which is 24.5 grams. Okay, that's for A. And what about B? Mass of zinc nitrate that could be recovered from the solutions. So amount of zinc nitrate produced here. So based on the limiting reagent, which is 0.75, mole ratio is 2 to 1 as usual, same thing, 2 to 1. Therefore, I have 0.375 moles of zinc nitrate because you divide by 2. And then what to do next? The moles. Okay. And from these moles, how to convert it into the mass of zinc nitrate that can be recovered times the molar mass of zinc nitrate. Okay, so molar mass of zinc nitrate I've calculated here is 189.4. So end up you're getting 71.03 grams of zinc nitrate can be recovered from the solution. So this is 71.03 is the answer for B. Okay, so that's part B. So we solve A and B here. Moving on, last questions. 22. Now a solution containing 200 ml of 1 mole per liter sodium carbonate. Okay, 200 ml, 1 mole per liter sodium carbonate. Okay, and then also 200 ml, 1 mole per liter barium chloride. All right, and then will a precipitate form? If so, write an equation for the reaction. So I'm answering A. Will a precipitate form? Write the equations. Sodium carbonate plus barium chloride. And what do you expect to get? Exchange them. Sodium chloride plus barium carbonate. Okay. Any precipitate form here? Let me balance it first. Yep, that's balanced. So yeah, this is the precipitate. Barium carbonate is the precipitate form, so your answer is yes. And you write these balanced equations out. With the state symbol, if possible, guys, this is aqueous, this is aqueous, this is aqueous as well. All right. All right. Part B. Calculate the mass of precipitate. So you need to calculate the mass of the precipitate. Let me do the calculation for B. Okay, let me redo it again for part B. Okay, sodium carbonate. Sorry, guys, I have to rewrite it again. Barium chloride changing into barium carbonate, which is a solid, plus 2 NaCl. Okay, this is balance equations, and what is the mole for each? Sodium carbonate used is 1 times 200 over 1000, which is 0.2 moles. Same goes to barium carbonate because everything is the same. 1 times 200 over 1000, you get 0.2 moles. So there's no limiting and excess. Both are the same. So I'll expect everything converted into the product. All right. So in this case, what is the mass of the precipitate? 0.2, 0.2. The ratio is 1, 1, 1. So 0.2 mole as well. Right? And then you're going to use 0.2 mole multiplied with the molar mass of barium carbonate, which is 197.3. Please calculate, double check, and you will get 39.46 grams of the precipitate, which is barium carbonate. Okay, that's the answer for B. Make sense? All right. Part C. Let me erase only certain things. Let me erase the mole, so it should be 0.2 for both. So that's part B. Now I'm in part C. All right. Part C. Determine the concentration of any remaining ions in solutions. Now, this is much easier because we have no limiting in excess. So I have 0.2, 0.2. This is fully converted into solid barium carbonate. So no more barium, no more carbonate. All turned into a solid. So the only remaining ions here will be sodium and chloride. So what is the mole of sodium? Mole of sodium should be, I have 0.2 moles of sodium carbonate. I have a 2 here, so 0.2 times 2 is 0.4 moles of sodium. And what is the mole of chlorides? Again, 1, you have 2 Cl inside, 1 barium chloride, I have 2 Cl. So 0.2 mole, I should have 0.4 moles of chlorides. Okay, barium and carbonates all converted into solid. So what is the concentration now? I have the moles. So moles equals to mv or 1000. M is the concentration. V is 200 plus 200 because it makes them. So 400 ml over 1000. Same goes to this M 400 over 1000. And then both giving you the same answer, which is 1 mole per dm cube or 1 mole per liter. Yes. Okay, 1 mole per liter. That's it. So this will be the answer for part C, both sharing the same concentration of 1 mole per liter. All right. Yep, that's all for the whole tutorial 3. Again, please raise your concern or whatever questions you would like to ask during the tutorial sessions. I'll be seeing you soon. All right. Thank you for watching the video. Bye.